one of the things that I want to do is I also want to talk about the qualitative aspect of linear optimization functions and non-linear optimization problems. Okay, so let me quickly go back to the the unique solution plot that we have here. So which is the plot that we had this. As turns out, when you have a linear problem, interestingly, when you have problem like this, you have a feasible region, which in this case was defined by this A, B, and then you have to have this this region right here. This point has to be to C, A, B, C, D, E defines the feasible region. It turns out there is a beautiful theorem in linear programming that tells you that if the problem is linear, then the solution is always the optimal solution is always going to lie on the boundary of the feasible region. And what it means is the optimal solution is only going to lie on A, B, C, D, and E. It's not going to be lying in the interior of the feasible region. It's going to lie on the boundary. And this is a very valuable information because we don't need to search for anything inside. We need to just focus on this whole line segment A, B, B to C, C to D, D to E, and E to A, and look around that line, this set of 5 lines, and we will be able to find the optimal solutions. Okay. In fact, the most important things we are looking is probably the vertices that defines this region. And if you have an intelligent approach which can focus on basically looking at this boundary region and more importantly at the vertex of that is defining this boundary region, then you can solve a linear optimization problem very, very quickly. And that's the beauty of any linear optimization problem, and that's why you have very, very efficient algorithm in linear programming that solve for this class of problems, and they are intelligently looking only at the boundary to solve for this class of problems. But it turns out that that is not necessarily the case for non-linear problem. Okay, and this is something that I want to discuss qualitatively, and this is a very, very important concept that in linear programming the solution is going to lie on the boundary of the feasible region, but in non-linear problem that is not the case, and the problem is more complicated, and then you need a more general approaches, more specific approaches for non-linear optimization problem. So let's look into an optimization problem which is non-linear and see qualitatively what happens. Okay, and how we can see that the location of the optimal solution could not be guaranteed on the boundary. Okay, so here is an example problem that I want to begin with, where we have a non-linear objective function. So this is an objective function which is non-linear, and we have two variable problem, and then we have again constraints which are linear. Okay, so one thing that I also want to remark, that it does not matter whether one of your objective function or one of your constraint is non-linear, then the overall problem is non-linear. Okay, if all the function including the objective function and the constraint functions if they are linear, then you have a linear programming problem. If only one of the objective function or the constraint function is non-linear, then that problem becomes a non-linear problem. All the other remaining could be linear, but that does not affect. That still is a non-linear problem, and this is the important concept that you need to know. So you will see that in this case we have an objective function which is non-linear, but the constraint functions are going to be linear. But even that's the case, the overall optimization problem that we are focusing on is essentially a non-linear optimization problem. Okay, so here are the two constraints. Here is the 4, and we have 6 constraints here. So what we want to do, we want to probably convert them into negative null form. If you plot them, this is how this plot is going to look like, right? So we have like from z0 to different constraint, and we have plotted, right? So one of the things that we can do is we can see what is the feasible region. Okay, so if you look into this problem, the feasible region is defined by this boundary. So this point, this point, this point, this point, and so on. So let me mark that. So I can write this as A, this as B, this as C, and this as D. Okay, so A, B, C, D defines essentially the feasible region, and the region inside that A, B, C, D polygon is essentially a feasible solution, right? So what we need to do is we need to find out solution which basically lies and which is also optimal in the sense. So let's go ahead and let's try to plot the objective function. So if you look into the objective function which we have here, looking at this equation, the minimum value of this objective function is going to lie at 3.5 and 4, and this is a quick check that you can do, and that's why you will see when we are plotting this objective function, which is basically being plotted by this counter, this point is going to be 3.5 and 4, right? So this is where the objective function value is going to lie, right? And this is going to expand. The objective, this is where it will be minimal, but it's going to expand, and the objective function values are going to start increasing as we move geometrically outside this point, right? So we can go, and this will be another counter that we can plot, and that counter value I have will be more than the counter plots that are inside, right? But one thing that I want to notice is this point is not in the feasible region. The feasible region is defined by ABC. The point has to lie in it. So what we need to do, we need to start drawing the contours which are now moving us towards the feasible region. So this, all the set of lines that we have already plotted in the light blue is not feasible. So we need to keep increasing and keep moving, and if we keep doing that, we will have one counter which basically touches, and which will be a counter like this, which will be touched, which will just be touching the feasible region right here, right, of the boundary, that will have the least function value while being feasible. Here we have function values which are smaller than what we have for this counter, but they are not feasible. But this is the one which has the least objective function value while being feasible. Whereas if you take this counter, okay, that is there is a solution which is feasible here, but that has more objective function value than what we have for this counter. And that's how we will determine the optimal solution for this overall problem. So this will be the location of the optimal solution. Okay, so in this case, what happens, it turns out that the optimal solution lies on the boundary of ABCD, right? So this is very, very similar to what we have done previously, where we have the solution which is lying on the objective function boundary ABCD, and the solution is on the polygon itself that is defining the feasible region, and the polygon was because we had essentially a set of linear equations, right? So right here we have the optimal solution, right here we have the optimal solution location. This point has an optimal solution, and that lies on the boundary of the polygon itself. Okay, but if we choose a different objective function, not the one that we have listed, and let's say we have the same set of constraints which defines this feasible region, which is given by A, B, C, D, but if we change the objective function from what we have here, which is this 10x1 minus 3.5 square plus 20x2 minus 4, and change that slightly, but we have the same set of constraints, right? And let's say if we had this is the new objective function, where we are minimizing this function, right? So now you will see that the one of the locations where it will have the minimal value is going to be 2, 3. Okay, so if you look into 2, 3, that's where this point is. This is where it will have a 0 function value. Okay, the function value will be 0, and any other point the function value will be more than 0, right? Now if I look into this solution, this becomes my optimal solution for the second objective function. Why? Because this is the point where we have the least objective function value while being in the feasible region. Okay, so that's why this will be an optimal solution for the case where this is the objective function, whereas the constraints are same as the previous problem that we are discussing. Now if you look into this solution does not lie on the boundary of A, B, and C and D. This is inside the boundary. And this is the beauty or the complexity of the nonlinear optimal solution. The nonlinear optimal solutions, optimization problems, it's very hard to exactly say where is the location of the optimal problem. In the linear case, where you have the objective functions and all the constraints linear, you know that your solution is going to lie on the polygon that is defining the boundary, which is in this case, if we had an objective function that was linear, then in that case it would have to lie on A, B, C, D, E. But now since our objective functions are non-linear, where the constraints are linear, we can see one case. For this case, for the first problem in the previous slide, the objective function value optimal lies here, whereas for the case where the objective function is this, whereas the same constraint, the optimal solution lies here. Okay, so in case of non-linear optimization problem, it is very, very hard to pinpoint where the optimal solution is going to lie, and we cannot guarantee. And typically that is why the non-linear optimization problems are more complex than the linear optimization function. So with that, we will stop this lecture, and we will again come back with the next class where we are going to deal with different classification and the different nature of the optimization problem. Thank you.